No. Okay. That's everything. It's much warmer in here than it is in my office. This is like an ice box. Okay, so make sure you're doing your seating chart. Make sure you're doing your seating chart. You've been signed out. Is it still running? Yeah. Okay. All right, we got one more minute. So there is a wasp hanging out in the classroom, kind of in the back by the lights. So I asked custodians to come and bring some wasp spray or something. So if they come in the middle of class, that's what it's for. So I guess we'll try to keep an eye on it. All right, so where does spaghetti go to dance? To the meatball. To the meatball. Okay. A few announcements. Your grades are posted from the last exam. I will hand back those exams at our next class period. So on Thursday, I'll hand back the exams, but your grades are posted. So everybody will get to see theirs next time. So this is the last exam before drop day, because drop day is the Tuesday after Thanksgiving, so the November 30th. So this is your last exam before drop day. So this is kind of the most up-to-date your grade is going to be before drop day. So if you need that information to make a decision, the grades are posted. So I updated iClicker, I updated homework, and I updated the exams. Okay. Yes. Was this test also? Yes, it was. It was. And you'll see him. You'll see him when you get him back on Thursday. I'll talk about that. And then because the next exam is not until like the very next week after drop day. So like it's the Tuesday after that. Tuesday, it's gotta be like the 7th or something like that, right? So if you're thinking about dropping, come and talk to me, and I'll help you out and help you make that decision.
The lowest test rates drop.
The lowest test grade will be dropped once all 4 exam scores are in. So if you want to calculate your own score, if you think you're going to do better on the 4th exam than one of the previous, you can download the grade calculator, the final grade calculator. You have to download it. You can't just edit it. But you can download it and you can calculate what you think you might get, right? But that's all hoping you do better than your lowest other exam, okay? All right, any other questions before we jump in? Got your eye clickers? Take your eye clickers out. Please use your mask to cover your mouth and your nose. I know it's kind of warm in here today. Don't know what's up with that. Okay. So, oh, I'm closing the wrong thing. Here we go. Okay. All right. So get your eye clickers out. Okay. And this is going to get really important. So this is a little bit of a review and a little bit of what you need this time. So a single water molecule can make a maximum of blank hydrogen bonds. How many hydrogen bonds? And I gave you water. You should know how to draw water. I gave it to you. How many hydrogen bonds can it make? Remember, I'm going to cut it off at 1 minute. So you have about 10 seconds left. Okay, you can turn and talk to the people around you. Come up with another answer. And don't forget to click in again once you make that decision. And at 45 seconds, I'll cut it off again. Five seconds. Make sure you've clicked in again. Okay, so what did we say? All right, so it is 4. It is 4. So let's talk about that. Why is it 4? What is missing on my picture of water? There's something missing. This is pretty good, but it's not perfect. What am I missing on this? Remember when I asked you to draw water, right? Remember I've asked you that a couple of times now? This picture is missing something. What is it missing? Why is water amazing? Why is water so cool? Because it's polar. So how do I indicate that this molecule is polar? There are a couple of different ways that you could do it. What could you do? You could do the individual arrows, right? So what would I point at? I would point at oxygen. So I have 2 partial charged bonds, right? And so that gives me an overall dipole moment in the molecule that looks like this, right? What's the other way that you could do it? That is completely correct. What is the other way that you could do it? You could just say this is partial negative, this is partial positive, this is partial positive, right? It's not a full charge, it's a partial charge. Okay, so now, where are my hydrogen bonds? This hydrogen is a donor or acceptor? This is a donor. Most people see the hydrogens and know that these are donors. That's true. But what else do we have? We have electronegative atom with 2 lone pairs. So each lone pair is an acceptor site. So we have 2 acceptor sites and 2 donor sites. That's what makes water so cool. It can make all these interactions. So when you turn water into ice, right, because you have so many hydrogen bond possibilities, the water molecules have to arrange themselves in a crystal structure where they're very highly organized. So the molecules actually spread farther apart when they go from the liquid to the solid form. And that's why ice floats. It's really cool. You know that no other substance floats in the liquid of its own substance, right? Because ice is water. So ice floats in water. It's kind of crazy. No other substance does that. Anyway, why do I think water is cool? It's so cool. All right, why do I have a blank one? What is going on? Come on. Well, that's not good. Okay. Hello, computer. Let's try to open it up again. Or y'all are just going to get one eye clicker question today. Goodness, they need to put the AC on, huh? Okay, let's see. Okay. All right, here we go. Which of the following solutes would you expect to dissolve in water? So what do you think is going to dissolve in water? I just told you all about water. What is going to dissolve in water? One minute. I'm asking them to turn the AC on over here. So 5 seconds. Okay. Turn and talk. Come up with another answer. "45 seconds. Go ahead and talk. Don't forget to ring in again. 10 seconds. Okay, so what's the rule for dissolving? What's the rule? Talked about this. Like, how does it go? Like dissolves like. So what would you expect to dissolve in water? What is water? Polar, non-polar? Polar. So what is going to dissolve in water? Things that are polar. Is hexane polar? That's non-polar. Is CCl4 polar? Be careful with this one. CCl4, carbon and chlorine, do they have different electronegativity values? Absolutely. But this is a tetrahedral molecule, right? So while each of the bonds is polar, overall this molecule is non-polar because it's symmetric. Okay, so that's a non-polar substance. How about C? Absolutely, right? I have two lone pairs. So I have two acceptor sites and a donor site for hydrogen bonding. So this is absolutely polar. How about pentane? Non-polar. If you're just carbons and hydrogens, you're non-polar. So you should have said C. Okay, 1, 2, 3. So you should have said C. Good. Very good. Awesome. Awesome. Okay, so that's a really great intro for what we're going to talk about in chapter 8. If I can get out of here. Okay. All right, because what we're going to talk about is solution chemistry, how things dissolve, excuse me, and things like that. So whenever we're talking about, is something going to dissolve in something else, right? That doesn't sound like good science words, right? Does something dissolve in something else? That sounds really arbitrary, right? So we have to use the correct terminology. So if you're going to take a substance and dissolve it into something else, you have two things. One is going to be a lot of it, and one's only going to be a little bit, right? So whenever you're doing this, the solute is what you have less of. The solvent is what you have more of. What is the universal solvent? Universal solvent is equal to water. Okay. Okay, so let's look at some examples here. Identify the solute and solvent in the solutions composed of the following. So I'm going to put solute. I'm going to put solvent. Right? Okay. So helio-X, a breathing gas that is 79% helium, 21% O2 for patients who have difficulty breathing. Now this is really, really cool because normal air is about 78% nitrogen and it's about 21% oxygen. So if you look on the periodic table, look at nitrogen. What's the atomic mass of nitrogen? What's the atomic mass? 14.01 AMU, right? Okay, how about for helium? 4.00 AMU. So what is more dense, nitrogen or helium? Nitrogen is more dense. So if you replace the nitrogen in normal air, so this is normal air. If you replace this nitrogen with helium, what you're going to end up doing is reducing the density of the gas that the person has to breathe, right? They only really want the oxygen. So if we can reduce the density of the gas that they have to breathe, it's easier for them to inhale and exhale. So that's why we use helio-X. So in helio-X, what is the solute? Remember, solute is what we have less of. O2. What is the solvent? Helium. In normal air, would you have put helium? No, you put nitrogen. Okay. So how about B? Children's Tylenol oral suspension containing 160 milligrams acetaminophen per 5 grams of water. So what do we have less of? Acetaminophen, TAM. And then what do we have more of? By a lot, right? That's 5 grams versus 160 milligrams, right? Milligrams is 1,000 times less than grams. Okay. All right. A tin, I don't even know what this is like I don't know how to pronounce this. This is a little container that that you use to dissolve things. But so it contains a small amount of an herbal remedy dissolved in alcohol. So what's less? The herbal remedy, whatever herb you have. And then what's the greater volume? The alcohol. AlCOHOL. Okay. So that's really easy. All you have to do is which one is more than the other. All right. Now, there are a couple of different things that you can make when you dissolve or you put one thing inside of another, right? So when you watch the lesson online, so what are our big three? Throw one out there. You might have to have more eye clicker questions. A solution. A solution. What else? A colloid. And the third one, a suspension. S-U-S-P-E-N-S-I-O-N. Suspension. Okay. I left this extra column here because I want to use this space. Okay. So I'm going to say this is both solution and colloid because they have some common properties. So let's see if we can define each of the three and figure out ways to separate them. So a solution, what is a characteristic of a solution? It must be clear. Must be clear. Give me an example. Salt water. So I would say black or plus sugar coffee, right? Now, if you add milk, are you still a solution? Are you not? So you got to be careful about that. Okay, tell me about a colloid. So not transparent. Okay, what else? There's something about a colloid, like you put stuff in, but it doesn't dissolve. So you can say has substances that do not dissolve, right? Therefore, it's not transparent. So some of the examples of things that will not dissolve are proteins, fats, right? What do fats do? Right? Soaps are made up of fats. What do fats do when you put them in water? They make micelles. Remember that? Micelles. Okay. So colloids have substances that do not dissolve like proteins and fats. Therefore, they are not transparent. So this would be something like milk, cream, right? Those kinds of things. And usually these are small particle size. So if they're a small particle, even though they don't dissolve, they're still suspended equally, right? So even though a colloid is not a solution, what do colloids and solutions have in common? That third column, what do they have in common? They both what? So a colloid will not dissolve, a solution does dissolve. But here's a cool thing. Even though a colloid doesn't dissolve, it's still uniform composition because the particles are small in size. So it makes them both homogeneous mixtures. So homogeneous is a uniform composition. So like if you set out a solution or a colloid on the counter, it would not settle. So would not settle over time. Right? If you put milk out on the counter, do you end up with a layer of milk? Do you have to shake your milk every time you go to pour it out? No, you don't, right? So it's a colloid. So now that leads us into what's the difference between a suspension? Guess what happens in a suspension? The particles will settle. So particles are large and will settle over time. So blood is an example of this, right? The red blood cells are heavy and they will eventually settle to the bottom if you take it out on the tube, right? Muddy water. Have you ever seen a tube in high school? Did you ever do this in like earth science or environmental science, where it was a river tube? And so it had water and it had the different sediment. So it had really fine particles to really big particles. And if you shook it up and then you set it down, the really heavy stuff would go to the bottom first. Then the size would get smaller and smaller until the very fine silt would take like days to settle. But eventually you'd have clear water at the top. You ever do that? Some people did. Yeah, it's really cool. Okay, so now do we understand the difference between these three? Okay, let's go up and try to answer some questions. Okay, identify the following solutions or colloids. 5% albumin, a protein IV replacement fluid. So this is a protein in water. Tell me about a protein in water. It's a colloid, right? We said a colloid, if you come down here, right, are proteins that do not dissolve. So that's a colloid. The electrolyte replacement IV fluid lactated Ringer's solution. What's an electrolyte? Have you seen Gatorade, Powerade, you know, all these electrolytes, and you know, they're trying to sell it to you, right? You could just drink water, you'd be fine. Unless you do extreme sports, water's great. But what does that electrolyte refer to? Salt. It's different kinds of salt that they put into Powerade, Gatorade, right? And so what happens if you have salt, NaCl, and you put it in water? What happens? The NaCl will break up into what? Na plus, Cl minus. These are electrolytes. So are they solutions or colloids? Solution. And it really told you that, right? It told you it in the question that it's a solution, but you should know that. All right, D5W, a 5% dextrose IV fluid. What is dextrose? It's a sugar. Remember when we drew sugars? What was bound to all of these carbons? Either hydrogens or hydroxyls. What's up with a hydroxyl? They can participate in what? Hydrogen bonding. So are they polar or non-polar? Polar. Not the whole molecule is not polar, but there are parts of the molecule that are polar. So will it dissolve in water? Yes. So what kind of a substance is it? Did you see how hard it was for me not to say solution? I had to pause really long and not say solution. Okay. So that's really easy, right? Now, did I not? Did I really do all? I did it in 8.6. Oh, I'm just writing. Oh, that's me and mine. I never have enough room to do anything, right? Can I? No, I can't get rid of it. Okay. So the next thing to talk about are when we dissolve something, you say you have salt, right? And you just shake a little bit of salt into your water. Could you put more salt into that water and it would continue to dissolve? Sure, right? But as you add more and more and more and more and more salt, eventually what's going to happen? Eventually, you're going to add so much salt that you will saturate the solution and some of the salt will not dissolve, right? That's a saturated solution. So what you have to kind of remember about a saturated solution is that you actually don't have a piece that is not dissolving, right? So if we put salt into our little beaker here of water, we put salt in, so salt goes in, right? We put so much salt that we saturate it. The next piece of salt that we add in, I say does not dissolve, but actually it does. Actually, part of it dissolves and then salt that was dissolved in the solution recrystallizes. So it actually kind of cycles, right? So you have the same amount of salt that will not dissolve, but it kind of cycles. So that's one thing you got to kind of keep in mind. So a piece of rock salt that does not change in size when added to a salt solution. So this is exactly what we just described. Is that a saturated solution? We had a salt solution. We added a big chunk of salt to it and it didn't dissolve. Saturated or unsaturated? Saturated. You can't put any more in. A teaspoon of honey that dissolves in hot tea. No. If it's dissolving, then it's not saturated yet. But there's a way to make something super saturated. Have you heard of that before? A super saturated solution? That means that at room temperature, if you keep adding stuff to it, it won't dissolve anymore. It's saturated. But if I change a condition, like I change the temperature, I can make more of that saturated solution, more of that solute go into the solution. So I can make a saturated, I can force a saturated solution, right? And so when we talk about things that will change our solubility, temperature is a big one, right? So I want you to think about two things. Let me extend the page and I want to talk down here. So if I want to talk about things that are going to change solubility, one thing that I can talk about is temperature, right? So I want you to think about making tea. If you want to make the perfect iced tea, right? What's the old school way to make iced tea? You get the tea bags and you put it in what kind of water? Cold water? No, hot water, right? Really hot water, not quite boiling, but really hot water. And before that tea gets cold, what do you add to it? Real sugar, right? Okay, that's like the old school way. Why do you want to add the tea bags and the sugar to the warm water? So it will dissolve better. So if I increase temperature, think about this is my tea. This is my tea example, right? Put yourself that little note. What happens to my solubility, B-I-L-I-T-Y, of a solid, right? So we'll say this is sugar, into a liquid. This is the water / tea, right? So what would happen? Would my solubility increase or decrease? It would increase. Solubility would increase. That's exactly right. Okay. Now, what happens if I increase the temperature on a liquid, so solubility of a gas into a liquid? This is the next thing I want to talk about. How many of you guys enjoy a nice Diet Coke, right? It's nice, right? Okay, now listen. What happens when I pop the top on my Diet Coke? What do you hear? That's a release of pressure, right? So this can of nice, delicious, cold Diet Coke is under a certain amount of pressure, right? What happens if you live in Louisiana and you accidentally leave a Coke in your car and it gets really hot? It's going to explode. Don't do it. It's going to explode. Why is it going to explode? What happened to the solubility of my gas inside of the liquid? Do you think more gas went into solution? No. The whole point is when it got hot, this can went under a lot of pressure, more pressure than it was under right before I popped the top, right? How did it go under more pressure? Because the gas left the liquid and now it's pushing on the sides of the container, so much so that the container is going to explode. So what happens to solubility of a gas in a liquid when I increase temperature? Does it go up or does it go down? Goes down. Do you see how it's different depending on what kind of a solution you dissolve in and what kind of a solute you are, right? Same thing's true. What if I just pop this top on this Diet Coke? Oh, it's so delicious, right? But I gotta go to class. What should I do with it? Should I leave it on my desk or should I put it in the fridge? Why should I put it in the fridge? Because as I decrease the temperature, what happens to my solubility? I increase solubility of a gas into a liquid. So what's that telling me? If I put my Diet Coke in the fridge, it's going to be fizzy still, right? Have you noticed that? If you open a soda and you have to go and do something else, if you leave it out on the counter, what happens when you get back? It's flat, it sucks, right? But if you pop it in the fridge, what happens? It stays soluble. Isn't that awesome? Now you know why? Okay, so remember this. This is your Coke example, right? So your gas. When we talk about the gas in my Diet Coke, what kind of gas is in here? It's carbonated, CO2, and I'll say soda / water, right? So if you can remember Diet Coke and you can remember iced tea, you know all your solubility rules. Isn't that kind of cool? Okay, I'm gonna have a little bit of this. It's just wrong to let it completely go because I teach for the next 3 hours, so it's gonna be flat. All right, fill in the blank in the statements with the words increase or decrease or stay the same. Okay, we're gonna apply the rules we just wrote. If the temperature of a solution decreases, so temperature goes down, the solubility of a gaseous solute will what? Increase. Right? Which example is that? This is my Diet Coke, right? What's my favorite drink? Now y'all know. If the temperature of a solution decreases, the solubility of a solid solute will do what? Decrease. This is the opposite. So what example is this? This is my sugar in tea. Doesn't that drive you crazy though? You're at a restaurant, you know, and you put like the artificial sweetener or the regular sugar in your iced tea and you swirl it around real quick, but you're busy talking with your friends, right? And your straw is at the bottom of your iced tea and you go to take a drink of it. And what does it taste like? Just sweet, right? Because it didn't really dissolve because the temperature is what? Cold. So cool, right? Didn't you know that chemistry was going to be cool? All right, if the pressure above a solution decreases, the solubility of the gaseous solute will do what? Okay, so this is talking about pressure, right? So why do sodas come pressurized? Remember you heard that little psh when I opened it? Why do they come pressurized? If Diet Coke were packaged without being under pressure, my first sip, would it feel all bubbly on my tongue? Nope. And soda companies would lose lots of money, right? So if the pressure decreases, so if pressure goes down, what do you think is going to happen to our gaseous carbon dioxide in my Diet Coke? If I release the pressure, what I just did, what's happening to the CO2 right now? Can you see it just leaving the can? And I'm just so sad, you know, right? Okay, so what's going to happen to the solubility? It will decrease. This is our Diet Coke, right? If you can equate these things to things that happen in your daily lives, it's going to make a lot more sense. Okay. All right. Explain what's happening in the following situations in terms of solubility. Fish die in a lake that is heated with water from a power plant cooling tower. What's happening? These poor fish. We increase the temperature of the water. What does that do? Are there gases dissolved in water that fish live in? What kind of gas? Not carbon dioxide, but oxygen. So if we increase the temperature of the water, now we're going to decrease the solubility, so LU, of oxygen, O2, right? Oxygen is one of those ones that doesn't like to hang out by itself, so it's O2, in the water. So the fish can't breathe. Can't breathe. They don't really breathe, but you know what I mean. Breathe and die. Poor fish. But that actually really happens. Okay, B. Crystals form in a jar of honey that has been sitting for several months. So what's happening here? You have a certain number of sugar crystals per volume. But if I just leave my jar out, just put it out on the counter, what's going to happen eventually? The water will what? Water in the jar will evaporate. Now what? I'm saturating my solution, but I'm not adding more solute. What am I doing? So solution will become saturated because what? Because we added more solute? No, because what? Because something happened to the solvent. What's the solvent? Water. So because we have lost solvent, right? It's all about the ratio of solute to solvent. So either you could add tons of extra solute or you could remove solvent. This is what happens if you have a pot of salt water, right? Let's say we had a pot of salt water It was really close to being saturated, but not quite. And I heat it to the point where it boils. Eventually, I'm going to come back to that pot, and what's going to be left? Just salt, because you evaporated the water. You removed the solvent. Same thing. C, a person receives oxygen through a breathing device. So I'm going to put it up top. So what happens in a breathing device? Like a ventilator. What does it change? Pressure. It changes pressure. That's exactly right. So we increase the pressure of the gas, right? In this case, which is O2. So that's one way that we can force more air in. What's the other way? Have you seen the little nasal cannulas that go up people's noses, right? Is that just regular air going in there? What is it? It's high concentration O2. So it's more than the normal 21%. So you increase the pressure of the gas, or you increase the concentration of O2, right? So we're increasing the solute. Either way, the person's getting more oxygen, right? Okay. So this is one example of that, right? So a hyperbaric oxygen chamber. This contains 100% oxygen rather than 20% oxygen found in air. So if you have somebody who has been exposed to carbon monoxide, here's the problem with carbon monoxide. Inside of your red blood cells, you have hemoglobin, right? Hemoglobin has 4 binding sites. Each molecule of hemoglobin has 4 binding sites and can bind to O2. So for one hemoglobin, you can bind to 4 oxygen molecules. And your red blood cells are like sacks of hemoglobin. That's all they do. They've even lost their nuclei because all they care about is carrying oxygen. So normally, right, you carry O2 to your cells. You drop off the O2, you pick up what? What's the waste product gas? Carbon dioxide, right? Goes to your lungs. When you breathe in, you exchange that O2 and CO2, and you get to go on the trip again, right? That's how it works. So in carbon monoxide, the problem is that carbon monoxide binds to hemoglobin with a much higher affinity than O2 does. So even if you have take a breath and you take in both oxygen and carbon monoxide, your hemoglobin is only going to pick up carbon monoxide. That's why it's so dangerous, even in small amounts. So what you have to do is you have to put somebody in a chamber where there's nothing else there. It has to be all oxygen, right? The highest concentration oxygen possible. So the more O2 you put in, the more you're going to have a replacement of the carbon monoxide and the CO2. Oh, I can feel it getting cooler in here. Can y'all feel it? Yay, you could thank our secretary, Christy, for that. That's who I emailed. So she must have taken care of that for us. Okay, so if you have 100% O2, right? What you're in essence doing is changing the partial pressure of the gas. So when we talk about gases, we don't really talk about concentration. Concentration is something to do with liquids. So when we talk about gases, we talk about partial pressures. So if you have 100% O2, you have a very high partial pressure of O2. This is Henry's law. So more O2 is going to get picked up by the hemoglobin in the blood. Will be picked up by hemoglobin in the blood. which will replace the carbon monoxide. Right? So that you can't change the binding affinity. Carbon monoxide will bind with a higher affinity than oxygen. So what you have to do is change the concentration. When we talk about gases, we don't really say concentration, we really say partial pressures. And that's what Henry's law is about. Okay? But if you can think about it in terms of concentration, it's a great way to think about it. Okay. Now we're going to switch gears and we're going to go back to liquids. But let me, I'm going to use some of the space down here. We're going to talk about solutions, right? Okay. Is dissolving the same thing as the word disassociation? Those two things the same? They're not. They're not. So you have to be very careful about this. When we talk about things that disassociate, this means that they dissolve and they split apart. What have we talked about today that will disassociate? Electrolytes. So examples are NaCl, right? Because when you put it in water, will it dissolve? If I put salt in water, will it dissolve? Absolutely. Everybody in here knows that, right? But will it disassociate? And the answer is yes, it disassociates into Na plus and Cl minus. When something only dissolves, my example here is going to be sugar. Does sugar dissolve? Yes. Does it disassociate? No, I'm going to take this sugar molecule and it's still going to look the same, right? I've got OHs on it. OHs, right? CH, 2OH, right? It's got all these OHs on it. So it's highly soluble, but is it going to change its structure when we put it in water? No. So you can have things that dissolve, sugar. You can have things that dissolve and disassociate. Okay? So sugar is an example of something that will dissolve. Salt is an example of something that will dissolve. But disassociate, sugar will not disassociate, whereas salt will disassociate. So there are scientific words that we can use to describe this, right? We have a couple of them. So what if you have something that is a strong electrolyte? My example is NaCl is a strong electrolyte. It fully dissolves and disassociates 100% in solution. Right? So it completely breaks up. You have some things that are called weak electrolytes. Weak electrolytes, there are some salts that break up, but they don't completely break up, right? So if I had a strong electrolyte of NaCl, I would write a single arrow forward and I would write Na plus Cl minus, right? But I can have things that are weak electrolytes. Weak electrolytes are something that will dissolve, but only partially disassociate. So if you have X, Y, how do I say that it doesn't completely disassociate? Do I do that single arrow forward? No, I'm going to do this forward and reverse, which means that some of it will turn into X and Y, and they could be charged, right? but some of it is going to stay together. So it doesn't fully disassociate. And you can look at an equation and you can see that. A fully disassociate will be a straight arrow forward, and then a partial will have the back and forth, okay? Then you can have, the last thing you can have is a non-electrolyte. This can dissolve, but not disassociate. And the example of that is sugar, right? Sugar dissolves, but does not disassociate. So you have no, you could say no ions. Pretty good on that? So nice to have a drink while I teach today. All right, so let's go on to the questions about them. Predict if the following will fully disassociate, partially disassociate, or not disassociate when dissolved in water. Now, when we look at these things, we have to be given a little bit of information. So we're given a sodium sulfate, a strong electrolyte. So this is a solid that's a strong electrolyte, and we put it in water. What is going to happen? Is it going to disassociate fully, partially, or will it not at all? By definition, a strong electrolyte will what? Fully disassociate. Ethyl alcohol, a non-electrolyte. This is not. We see that we have some polar parts to it, so it will dissolve in water, but it will not disassociate. It will not change its formula. Hypochlorous acid, a weak electrolyte. Partial. Once you know those definitions, you can answer those, right? Okay, so now we need to be able to write. I didn't do this. Did I? I didn't do this on the video. I must have not remembered to clear it. Oh, that's terrible. That's a pain in the butt. Sorry, y'all. Okay. Did I clear? Can I highlight more than this at once? No. Let's do this. Oh, how about undo? Edit, undo. Let's see. See, I just want to get rid of this. No. Guess I'm just going to have to erase. Sorry, y'all. Okay. The best laid plans, right? Okay, so when we're looking at these different types of compounds, what we have to be able to do is to look at them, say what's going to happen, and then express that in a chemical formula. Okay, so here we go. Provide the balanced equation for the hydration. What is hydration? I'm so thirsty, I need to take a drink of water. So this is anything where you add water to each compound that was in the problem that we did above. So the first one was sodium sulfate. Na2SO4, and it's a solid. We're going to add that to what? Water. What state of matter is water? It's a liquid. Okay. Now, if it's a strong electrolyte, what kind of an arrow do I want to put? A single straight arrow. Now, sometimes your book will show it like this. Sometimes your book will show it, SO4S. It'll show the arrow and it'll put water on top of the arrow. Either way is the same thing. okay? It doesn't matter. You just have to be aware that they're both the same thing. Okay, so then what happens? If this is a strong electrolyte, what's going to happen? We're going to separate it, right? This is an ionic compound, right? We have a metal. This is our metal. And then what is SO4? A polyatomic. Do you need your best friend right now? You need your best friend. Go find your best friend. I need to know what this is going to turn into when I dissolve it in water. So this is basically the reverse of writing chemical equations, right? So I know that I'm going to have Na. I know that I'm going to have SO4, but I don't know what the charges are. So what's the charge on SO4? 2 minus. What's the charge on Na? So I have to go look at the periodic table. It'll be +1. And you could have done the reverse crossover where you see this subscript 2 becomes a -2. And there's no 1, but there really is a 1 there, right? It would be in parentheses. And you would go up here and that would be +1. You could do it either way. Okay, so now I'm not quite done with this because this really isn't in the right form. I have to add the 2 and I have to say what state of matter they're in. So what state of matter are they in? They are dissolved in water, so we call them AQ for aqueous. AQ for aqueous. Now, the question is this balanced? And let me erase all this stuff because it's got a little crazy, right? So you had Na2, SO4, solid. Are all my elements balanced? No. So what do I have for Na on the left? I have 2. What do I have for Na on the right? 1. That's not good. What do I have for sulfur on the left? 1. What do I have for oxygen? 4. What do I have for sulfur? 1. What do I have for oxygen? 4. So what's the only one I need to change? Sodium. So what can I do to balance this equation? Multiply by 2 to get 2. How do I do that? Can I put my 2 here? No, you can't do that. You can't do that. Where can I put a 2? In the front as a coefficient. So anytime you write a chemical equation, you must balance your chemical equations. Good. Okay, now we got to do ethyl alcohol, a non-electrolyte. So our ethyl alcohol, try to leave that one there. So this is B. Let's do a different color. Okay, so ethyl alcohol, CH3, CH2OH. And this is a liquid, right? Alcohol is a liquid. And we're going to dissolve it in water. What are we going to get? It's going to be the same thing, CH3, CH2OH. It's a non-electrolyte. That's not going to change. The only thing that's going to change is that we've now dissolved it in water. So what do we put for the state of matter when we dissolve it in water? Aqueous. Okay, is that all right? Okay, let's do C. C was hypochlorous acid, HClO, and it is aqueous. So now, if we say that it is a weak electrolyte, what do we have to do? We have to go back and forth, right? And we're going to add water. So what we're saying is some of this is going to disassociate and some of it's going to stay together. So how do acids disassociate? By basically losing hydrogens. So do you see my hydrogen over here? I'm going to pull off that hydrogen. When I pull off that hydrogen, it's going to be all by itself. But together in the compound, the whole molecule is neutral. So when I start separating things, what's going to happen? I'm now going to have things that are charged. So I want you to go look in your polyatomic ion table and find out what's the charge on ClO. This is a polyatomic ion. It's negative. It's absolutely negative. It's -1. So what must the charge on hydrogen be? +1. Are we done? No, we need 2 things. What 2 things am I missing? States of matter. I've dissolved it in water, so it's aqueous. And what else? I have to check, am I balanced? And am I balanced? Yes, I am. Okay. Feel pretty good about that? Okay. All right. See, this is so terrible. And then next time I'm going to close. I need to do this again right before my next class comes in. Okay. So for the following ionic compounds, they're ionic compounds. So what are they going to do? They're going to dissolve, and they're ionic. So they're going to, at some point, disassociate, right? Turn into things with charges. So ionic compounds disassociate. I'm going to assume for this problem, I'm going to assume 100% dissociation. It's not always true, but for this, I'm telling you to assume that. So I need to write a balanced equation for their hydration in water. So let's pick up A. FeCl3. I'm going to draw my arrow, and I'm going to put water. And I'm going to assume 100% dissociation, so I'm only drawing one single arrow. So what am I going to disassociate into? Fe, and it's going to be aqueous, plus Cl, and it's going to be aqueous. What am I missing? Charges. Where's iron? Uh-oh, it's transition metal. Uh-oh. So what do I know about chlorine? Chlorine has to have one and one only charge. What is chlorine's charge? -1. So if I told you to go and write the formula, right? You wouldn't be able to write the formula unless I told you what the charge was for iron. So if I know that iron is FeCl3, and I know that this charge on the chlorine is -1, if I did the reverse crossover, it works, right? So now I can just do that for this. So what's the charge on iron? +3. So I would have to tell you that was iron 3 chloride for you to write the formula. But because you already have the formula, you can figure out which ion of chlorine of iron it is. Excuse me. Does that make sense? Okay. All right. So now, oh, last thing. What else are we missing? Balancing. We need to balance it, right? So how do we balance this? I have 1 of iron on both sides, but on the left side, I have 3 chlorine. On the right, I have 1 chlorine. So I need to put a 3. So now I'm balanced. And I'm happy. Right? Okay. B. NaHCO3. We're going to put it into water. What are we going to get? And technically, if they don't give you a state of matter, you can assume solid. So you can assume these are solids that we're putting in. So what happens? This is an ionic compound. So I know I have a metal and a polyatomic. So if you have a polyatomic, you can go look up the charge, right? So I know I'm going to have sodium. I know it's going to be aqueous, and I know I'm going to add it to HCO3, and that's going to be aqueous. All I have to do is go in and find my charges. So what's my charge on HCO3? Should be -1. So then to make this whole molecule neutral, what's my charge on sodium? What? Be careful. HCO3 has a charge overall of -1. That means the whole polyatomic ion has a charge of -1. If I go look on the periodic table, what's the charge on sodium? +1. So if I do the crossover, it ends up with a 1 down there and a 1 down here. How do I write that formula? Na1, but we don't write the 1. HCO3, 1, but we don't write the 1. So be careful that you don't bring that 3 up to be sodium's charge. Sodium's charge is +1. Yeah. If I had something down here in parentheses, a 2, then you would bring that 2 up. But really in parentheses, what do I have? A 1. And then I just write this formula as NaHCO3. Okay. All right. Let's do C. Oh, are we balanced? Yeah, we are. We're balanced. Okay, C. K2SO4. We're going to assume a solid. We're going to put it in water. We're going to make potassium. It's going to be aqueous. And we got a polyatomic, SO4. It's going to be aqueous. So what are my charges? K is +1 or just a plus. Really, you just put a plus. You don't actually put the number unless you have more than 1. And then what is the charge on SO4? -2 or 2 negative. So am I balanced? No. What do I need to do? Put a 2 in front of the K. Okay. I need some room. Can I erase the first one and do the first one up there? I'm gonna erase that. Okay, so now D. CaNO3, 2. We're going to assume it's a solid. We're going to put it in water. And we're going to make what? Ionic. So put your metal. Your metal is calcium. It's going to be aqueous plus your NO3, which is your polyatomic, and it's going to be aqueous. Now, here's the question. What's the charge? Right? What's the charge? So if I look at calcium, I can just look on the periodic table, and I know calcium is a 2+. But I could have also said, okay, here's my 2. I can cross it over and put it at the top. So then what's my charge on NO3? -1, right? Because really there's a 1 here, so I could cross that over to the top to get a -1. Am I balanced? Erase it and rewrite it. CaNO3, 2. Am I balanced? I have 1 calcium here and 1 calcium here. But if you think of the polyatomic ion as a unit, I have 2 polyatomic ions here, and I only have 1 here. So what could I do? Just put a 2 here. Yeah? Okay. All right. I can't believe I'm gonna have to go in and erase every answer before we do that. This is so embarrassing. Okay. So the next thing we have to worry about is a lot of times when you give people electrolytes, right? It's very, very important that you give them the correct amount of an electrolyte. Because inside of our bloodstream, we have ions dissolved inside of our blood, right? Now, if you have a red blood cell, right? Here's my red blood cell. There's a certain amount of ion concentration outside, and there's a certain amount of ion concentration inside the red blood cell, right? What happens if I put lots of ions, and we'll just put them as blue dots, right? We'll put them as blue dots. I put lots and lots and lots and lots of ions in the person's bloodstream through an IV, lots of them. But in the red blood cell, there's only a few. What's going to happen? Now, the ions don't really move because they have to be transported through channels, but water moves freely. So water is going to move in order to equalize the concentration on both sides of the membrane. So what's going to happen? Water is going to do what? Go leave the cell or enter the cell? It's going to leave the cell. So this is why you can't drink salt water. Like if you're stranded on a desert island and all you have is salt water to drink, don't drink it. Collect rainwater. Do something else, but do not drink salt water. Because by drinking salt water, you are increasing the ion concentration in your bloodstream, and all of your red blood cells are going to shrivel up and die because all the water is going to leave those red blood cells. That's a problem. So if you give someone too high of a salt concentration of an IV, you can kill them. Same thing is true if your red blood cell, just go with me, it's a red blood cell, has a certain concentration of ions. And what if you give them an IV that has less ions than what's inside the cell? What's water going to do? Water is going to go in and the cell's going to pop. The cell's going to explode. Is that good for the patient? Nope. So a lot of times it doesn't really matter what the ion is. It just matters, is it a +1? Is it a +2, right? What is the equivalent charge? And that is going to determine what you have to give the patient. So this is what those equivalents are about. See how it says how many equivalents of Mg2+ are present in a solution that contains 2.5 moles of Mg2+. So when we talk about equivalents, we're talking about equivalent charge. Okay. So if you have 2.50 moles of Mg2+, how many charge equivalents are there? Right? So if I look at that and I say, I have 1 mole of Mg2+, what's the charge equivalent of that? How many charges are in 1 molecule of Mg? 2. So I have 2 equivalents Mg2+. So what's my equivalent charge? 2 times 2.5 is 5.00. Remember your sig figs. Equivalents. So it depends on what the charge is on the molecules that you are putting in someone's IV, what the overall charge is of the blood. The blood has to say a certain charge. If you change the charge, we got problems. If you change the concentration of ions, you've got problems. So you have to be very, very careful about what you give patients and what you don't give patients. All right, let's try some more. Oh my gosh. Okay. Whew. See if I can get rid of this. I'm going to be doing it in about 10 minutes before class, just fixing this stuff. Okay. All right, we have a 5% dextrose IV fluid. It contains 35 milli equivalents. What's a milli equivalent? It's like a milliliter, right? It's 1/1000th of an equivalent. It's the same thing, milliliter, millimole, milli equivalent. It just means milli. Of K plus per liter of solution. If a patient receives 235 milliliters of the IV solution, how many moles of K plus were delivered? So what do you want to start with? I want to start with what the IV fluid contained, right? So the IV fluid contains 35 milli equivalents of K plus. Per what? Per liter of solution, right? So if a patient receives 235 milliliters of the IV solution, so I can take this and I can multiply by the 235. But here's my problem. What's on the bottom here? If I put milliliters on top, will it cancel? So what do I have to do? I have to convert it. So what you can do is just put 235 milliliters there, right? You can do it as a fence post, it doesn't matter. And then you just multiply times a conversion factor. So you have 1,000 milliliters in 1 liter, right? So now my milliliters cancel and my liters cancel. So now I'm in milli equivalents. Now what? I need to get to moles of K plus, okay? So what do I have to do to get to moles of K plus? Well, I got to get rid of the milli equivalents, right? So I'm going to put milli equivalents on the bottom. Can I convert from milli equivalents to moles? No, I can convert from equivalents to moles, but not milli equivalents. So I know I have 1,000 milli equivalents in 1 equivalent. Now I've got equivalents. So what's my ratio of equivalents to moles of K plus? Well, look at the charge. What's the charge on K? +1. It's a +1. So that tells me that I have 1, for every 1 mole of K plus, I have 1 equivalent charge of K plus. So I can just put 1 and 1 there. So what do you get? What's your final answer? What do you get? 0. Should be really small. What do you get? I got 0.0082. Yes? No? All K plus. Okay. We'll pick up on 8.4 next time. Okay, let me see if I can erase this stuff for my next class. Y'all have a good rest of y'all day.